ये अगर मेरे किसी वहाँ पे लेक्चर में आए तो मैं भी कैसे इंट्रोडक्शन हकीकत ये है, ये जो टॉपिक मैंने तैयार किया है आपके लिए, ये मैंने पहले नहीं पढ़ा था, या एटलीस्ट इस तरह से नहीं पढ़ा था कि मैंने पढ़ाना है। मुझे इस पर थोड़ा टाइम लग गया तैयार करने में, एंड आई एम श्योर कि तैयारी में कुछ लूपहोल्स भी रह गए होंगे, चीज़ें होंगी। मैं एक्सपेक्ट कर रहा था सारिन को भी और प्रॉब्लली डॉक्टर मुदस्सर को भी, फॉर्चुनेटली वो दोनों नहीं है। That's a good news। क्योंकि अब होगा ये कि अब मैं वो चीज़ें जहाँ पे मुझे खुद कन्फ्यूजन है उनको मैं ही वेग आर्गुमेंट्स दे के निकल जाऊँगा। हाँ, आपके लिए ये हो सकता है कि आप वो जैसे कहते हैं उर्दू में मुकाबली निगाह रखें, चीज़ों को ज़रा गौर से देखते रहें और देखें कहाँ से बाईपास करने की कोशिश कर रहा है, वहाँ से पकड़ लें। So, क्योंकि कुछ चीज़ें हैं जो इसमें ऐसी हैं जो मैं घर से सोच के आया था कि इनको मैं वेग रख के निकल जाऊँगा आगे, और अगर आप उसको बिलीव करते रहे कि हाँ संताल देन सो देयर आर थिंग्स जिनको आप बस पकड़ लेना चाहिए, ये कैसे कह रहे हैं आप। सो लेट्स सी वेदर यू कैन सिमुलेट साइम और नॉट। ओके, मैं थोड़ा सा आपको बैकग्राउंड बता देता हूँ। ये जब मैंने तैयार करना शुरू किया ये टॉपिक, थोड़ा सा इसकी जो मज़ेदार स्टोरी है, मुझे 2 हफ्ते लगे इसके ऊपर। सो तो मुझे तो पास भी कॉल लेक्चर में गए, लेक्चर तैयार करना है। मैंने इनसे पूछा आप क्या कर चुके हैं, मैंने कहा मैं प्रूफ्स पढ़ा। सो आई थॉट थिंकिंग अबाउट प्रूफ सिस्टम्स, यानी जो प्रूफ करने के मैकेनिज्म्स होते हैं, व्हाट आर डिफरेंट मैकेनिज्म्स। जैसा कि आपने कुछ मैकेनिज्म्स पढ़े हुए हैं, जिसमें एक बहुत पावरफुल मैकेनिज्म है प्रूफ बाय कॉन्ट्रडिक्शन, एक मैकेनिज्म है प्रूफ बाय इंडक्शन, कुछ प्रूफ्स बाय कंस्ट्रक्शन भी होते हैं, यानी बिल्ड एन आर्गुमेंट और उसकी कंस्ट्रक्शन बिल्कुल क्लियर होती है, देन एट द एंड ऑफ द डे थिंग्स गॉट प्रूव्ड। सो हुआ ये कि जब मैंने ये पढ़ना शुरू किया तो कुछ चीज़ें ऐसी मुझे अपीयर हुई मेरे सामने जो मुझे पहले कभी पता नहीं थी। तो मुझे 2 रातें में मैंने सोया, लिटरली सिर्फ ये सोचता रहा कि क्या बात कर रहा था ये मैं आपको बताऊँगा इंशाल्लाह। मैं आपको कोशिश करूँगा एज सिंपल एज पॉसिबल करके बताऊँ, लेकिन जो फर्स्ट ग्लांस में मैंने चीज़ें देखी थी वो इतनी सिंपल मुझे नहीं लगती। देन दे गेट सिंप्लीफाइड एंड स्टफ लाइक दैट। तो मैं थोड़ा सा इसकी हिस्ट्री पे जाता हूँ। मैं आज आपको जो करवाने जा रहा हूँ, जो एंड में हम कंक्लूड करेंगे एट द वेरी लास्ट, लेट्स से 10 मिनट्स ऑफ द टॉक, उसका जो बैकग्राउंड है जो मैंने थोड़ी देर पहले आपको भी बताया। मैथमेटिक्स में स्टार्ट में सिंबल्स का या बहुत ही क्लियर स्टेटमेंट्स का यूज़ नहीं किया जाता। द स्टेटमेंट्स दे वर एक्सप्रेस्ड इन नेचुरल लैंग्वेज। नेचुरल लैंग्वेज की लाइक इंग्लिश, जर्मन एंड सो ऑन। सो पीपल राइट देयर सेंटेंसेस, व्हाटएवर दे क्लेम्स आर, उनके प्रूफ्स या जस्टिफिकेशन दे, इट इज आल्सो इन नेचुरल लैंग्वेज। सो नेचुरल लैंग्वेज का मसला ये है कि जब आप उसके बारे में आर्गूमेंट करें ना, तो उसको किसी भी तरफ मोल्ड किया जा सकता है। और नहीं, मैं तो असल में ये कह रहा था। तो इस तरह के आर्गूमेंटेशन जो है ना, वो काफ़ी ज़्यादा यानी यू कम अप विद अ क्लेम, यू एक्सप्रेस क्लेम इन अ वे कि जब उस पर काउंटर आर्गूमेंट्स आएंगे, यू कैन जस्ट आई मीन उसको क्या कहते हैं, रीस्टेट द क्लेम इन डिफरेंट वर्ड्स एंड यू से कि मैं असल में ये कह रहा था, ये भी यही है, वगैरह वगैरह। चीज़ें क्लियर नहीं थी। तो इन पर्टिकुलर ये जो बहुत बड़ी मूवमेंट शुरू हुई थी 19th सेंचुरी में, यार थिंग्स शुड बी स्टेटेड इन वेरी वेरी क्लियर मैनर विदाउट एम्बिग्विटी, एंड देन देयर शुड बी क्लियर रूल्स ऑफ इन्फ्रेंस, जिससे एक स्टेटमेंट से दूसरी को इन्फर किया जाए या डिड्यूस किया जाए, दूसरी को तीसरी से, एंड सो ऑन। एंड दीज स्टेप्स and that language जिसमें किसी भी claim को represent किया जाएगा, they should be very clear. There shouldn't be any ambiguity. सही है? So, और इसकी एक motivation इसके पीछे एक motivation थी जिसको कहा जाता logical positivism. Logical positivism ये चीज़ है कि so logical positivist उस बंदे को कहते हैं जो जिसका मानना ये है कि everything is in the reach of logic. So you can reason about anything in the universe, any phenomena, anything that is happening. So if you want to understand what is happening around, whatever that thing is, whatever that phenomena is, logic is the only tool. So these people, they were logical positivists, and that school of thought. So this concept is called logical positivism. ये जो logical positivists किस्म के लोग थे ना, जो हैं, ये कहते थे कि यार ये जो चीज़ें वेग हैं, ये जो चीज़ें हम बताते हैं कि I believe this, मेरा faith ये है, there is something called intuition and stuff. State them clearly and prove them through logic. Then we will listen to you, not otherwise. मैं summary बता रहा हूँ, history. सही है? But then there was another group who thought कि not every phenomena is in the reach of logic. Logic has its limits at the end of the day, and the things to be understood, the phenomena that are existing in the universe, they are beyond that. There are some things that are reachable. But when they come to these logical positivists, they say, okay, prove it. We will not agree otherwise. Make sense? और अब वो proof ये नहीं हो सकता, नहीं यार, मेरा ख्याल है पिछले 4 साल से तो आप देख रहे हैं, 4 करोड़ सालों से तो देख रहे हैं ऐसे ही. That's not. Make sense? ये जो logical positivists हैं, who thought, and that's a very fair thought, कि यार हर चीज़ को, हर phenomena को, हर state को, हर phenomena को पहले तो एक proposition में transform करें, जिसके साथ आप associate कर सकें true false claim की सूरत में लेके, and then there should be some rules जो उसको true या false assign करें, and all these things should be clear. So let's build a mathematical system, logical system, that is able to express anything in its language. So that system initially it consists of some symbols that is called, let me call that as mathematical language. Those symbols are used to represent or state any claim that is in some other language. You first have to translate that into mathematical language. And then there are some rules that are written in the same language. And then you conclude something that eventually is in the same. So let's build some language. So language consisting of some symbols, alphabet, say it, and rules. Okay. And this language should be expressive enough. It should have a power to express any phenomena. You come up with some phenomena, some claim about something. This mathematical system, it should state the same thing in its language, and then it can talk about this, staying in that system. Say it? So that was a kind of a movement that started in the 19th century. 19th century, this like 100 years ago, that movement takes the big jump. The key people in this movement, there are other people as well, but the key people are, one of them was Frege, one of them was Bertrand Russell. I guess you've heard his name. Bertrand Russell is most famous, I guess. Then there is another person called Whitehead, who is the teacher of Bertrand Russell. And then one more person David Hilbert. If you have also, so this David Hilbert is a person who defined magnitude of any vector. So this is a big name. In linear algebra, often if you have gone through linear algebra, you might have heard about Hilbert spaces. So Hilbert spaces are the spaces in which the vectors, they have magnitudes and vectors and directions. So you can associate to any vector. So the Hilbert is a big name again. Hilbert. Okay. What was done is the following. Frege ने शुरू किया, उसने कहा कि यार ये जो language है ना, this language should be the language of sets. Everything can be represented in sets. And then there are rules to combine the sets and talk about the sets, whether this set is contained in another set, whether this is an element of that set, and so on. So he thought a set theory, if I represent each and everything in the world as set, and then there are some rules to talk about the sets, and so this language consisting of sets, this should be very expressive. So Frege built this, or maybe rebuild this, or clarifies the set theory, and sent to Bertrand Russell for a review. Bertrand Russell went through the theory gave by Frege and replied that it has a problem. And that famous problem later on was denoted by Russell's paradox. And the problem was the following. Because Frege was saying that I can represent each and everything, well, thing is not just a physical thing, every phenomenon, maybe your imagination, anything. I can state that as set, and then I can talk in sets. And that will be a system. Everything else should be converted to it and should be talked in this. If that appears to be true, we will accept that, and not otherwise. So Russell just came up with the following imagination or a set. He said, because everything can be represented by a set, Russell said, okay, what if S is a set of all sets, S1, S2, several of these sets, where so S is set of several elements, each element itself is a set. S is set of sets. So this set contains every element as a set. So every set is an element here. But each of this element has a property that Si, which is an element in set S, does not contain itself. So Russell said, let's imagine set of all sets that are not members of themselves. We say a set contains itself if that set appears to be an element in that set as well. So let's think about some set like this. A set of all the sets where each set does not contain itself. We will pick all such sets, we will just place them in a bigger set, and that bigger set is called S. So far so good? Yes? No problem so far. Then Russell asks, does S contain S? S is also a set. It may be an element inside it. So that was the question. क्या S को contain करेगा? It's a beautiful thing about these. If S contains itself, then it should not. You see that? अगर S, so let's say, if S is an element of S, then S should not be an element of S, because all these elements, they are sets that are not containing themselves. Yes?
तो समझ नहीं आई
जी
आपने ऊपर वाली बात जो की थी कि S I contains itself, वो वाली बात.
So a set is a collection of certain things. What if a set contains a lot of collection, and in that collection, that set appears as well? You might have heard about recursion and stuff. Make sense? Well, if you say me, okay, write that one such set for me that contains itself and stuff. It may be very hard to do that, but let me just try to do something. A set of all the brackets, curly brackets, infinitely many of those, and then infinitely many of these, set of these things. That set contains itself. Yes?
Yes.
You can see that?
Yes.
Ah, that's a weird set, I mean. Coming up with a set with these kind of properties, and those sets are of practical interest, or they are wandering around everywhere, you can see everywhere. That is not the case. It's weird. And this is just one example I just found on the net. It's just one example. Which is still arguable whether it contains itself or not. People are just debating about it. Yes?
I think there should be no debate about this, क्योंकि अगर infinitely many brackets हैं, तो उनके आगे भी infinitely many brackets होंगे, तो question फिर ये बन जाएगा कि does infinity contain infinity?
Yes.
तो वो तो फिर कोई question नहीं हुआ ना.
So does an infinity contains infinity? ये question नहीं है.
मतलब ये एक paradox है, ये आंसर नहीं हो सकता unless हम उसे कोई value assign कर दें.
No. Without assigning a value, I will show it shortly. Actually, I will start from there. I will start writing math. I will start from there. There are infinities that are bigger than other infinities.
Sir,
Then how is that infinity?
But there is a way to define infinity and then.
We have heard of this definition of infinity, that infinity is a thing which is very far. Like एक definition हमने पढ़ी मैथ्स में कि infinity होती है जो बिल्कुल end पे होती है, you can't see it. जैसे हमने physics में देखा कि physics में जैसे हम gravity पढ़े थे तो उसमें infinity ये थी जो क्या कहते हैं उस जो काफ़ी दूर थी लेकिन we can still define it कि वो किस जगह तो definition अलग थी.
So yes, मैं आता हूँ.
सर आपने कहा कि एक सेट अपने आप को कंटेन कर देता है तो हर दुनिया का सेट अपने आप को कंटेन करता है.
Well, that's too philosophical. I don't know. For example,
सेट ऑफ
for example, give me another.
S is equal to मतलब सेट ऑफ मतलब सारे रियल नंबर्स का
Sorry?
रियल नंबर्स का सेट है.
So that contains itself. By the way, a set of real numbers is not set of sets. It is a set of numbers. So it can never contain itself. It is not a set of sets in the first place. मेरी बात समझ? So मेरा ख्याल इतना आसान नहीं है इसको करना. ये शायद आसान हो, लेकिन मुझे थोड़ा सा टाइम लगा इसमें. मुझे लगता है ये इतना सीधा नहीं है. हो सकता है आसान हो, I don't know.
सही जो आपने सेट लिखा है
ये
इस सेट के अंदर आपने लिखा है इसके अंदर कोई वैल्यू नहीं अभी आपने लिखी हुई इसका मतलब ये कि सेट के अंदर
Oh, that's a value, this curly bracket is a symbol. Why one is value and this curly bracket symbol is not a value? Why is
नहीं
that?
कर्ली ब्रैकेट जो है वो एक एम्प्टी सेट नहीं होगा. ये तो मतलब ये नहीं होगा कि एंड पे एक एम्प्टी सेट है उसके बाद सेट है.
So set of empty set is not empty.
यस
So it's not an
इसका
empty
मतलब
set.
ये है कि ध्यान में इसके एक एम्प्टी सेट
Maybe.
तो इसका मतलब ये है कि वो जो एम्प्टी सेट है वो सेट नहीं है. तो इसका मतलब ये है कि
Empty set is a set.
एम्प्टी सेट
Is a set.
वो ये सेट नहीं है.
ये empty set नहीं है.
यस
Yes.
तो इसके दरमियान में लेकिन एम्प्टी सेट है
Fine. Empty set is an element.
लेकिन वो इस मतलब वो इसको कंटेन नहीं करता एम्प्टी सेट
Empty set तो किसी की चीज को कंटेन नहीं करता.
तो वही ना तो
मुझे पता है।
इसका मतलब यही है कि एस जो है वो क्या कंटेन नहीं करता
ऐसा अपने आप को कंटेन नहीं करता.
Yes.
देखें, मैं अगर फॉर एग्जांपल इसमें से एक सबसेट उठाऊं, लेट मी जस्ट इमेजिन मैं इसमें से एक सबसेट उठाता, मैं इसमें से एक एलिमेंट उठाता. बाय द वे अगर आप और से देखें इसमें सिर्फ एक ही एलिमेंट है, इस पूरे सेट में सिर्फ एक ही एलिमेंट है, जो कि ये कटिंग प्लेसेस हैं जो शुरू हुई होंगी, एंड दैट होल थिंग इज वन एलिमेंट. अगर मैं इसको उठाऊं, दैट इज एस. मेक सेंस?
क्योंकि वो जो कर्ली वेक्टर्स है वो भी इनफिनिट टाइम्स है, वो बढ़ती जाएगी, इस वजह से वो ऐसे.
यस.
लेकिन एक पॉइंट ऐसा भी आ रहा है जहाँ पे वो एक खत्म नहीं होगी
कोई पॉइंट नहीं. अगर कोई पॉइंट ऐसा आ रहा है तो मैं इन्फिनिटी पे बड़ी तफसील से अच्छा बात करूँगा. कोई ऐसा पॉइंट नहीं आ रहा. एक ही एलिमेंट है, मुझे नहीं जब एक से ज़्यादा एलिमेंट्स होंगे यूनिकनेस तो प्रॉब्लम करते हैं.
उस केस में जब आपने हर सेट का एक सेट बनाया उसमें जो हर सेट है वो यूनिक है, कोई ऐसा सेट नहीं जिसमें
That's definition of set, yes. Okay, everybody with me? So just forget about this set for now and come back to this. If S really contains itself, then the way we define S, it should not contain S, because S is set of all sets, and those sets have properties they do not contain themselves. If S contains itself, then by definition, this element should not be placed in here. Yes? So, if S is an element of S, then S is not an element of S. That's first thing. Yes? According to definition. Second thing, if S does not contains S, then it should. Because S contains all the sets that are not elements of themselves. So why this is missing? Because S is not an element of S, so S qualifies to stay in here. Yes? And there was no answer from Frege to this question. And this question is later termed as Russell's paradox. It's a huge kind of. I have just read some papers that actually Frege was very annoyed after this question. Just blew everything. So yeah. Then Russell and Whitehead, they started writing these books called Principia Mathematica. They write 3 volumes of those, in which they define theory of types, which was continuing the work of Frege and building a formal system without contradictions. A system that does not drive contradiction. A system that is not able to drive a statement and its opposite as well. They started doing this. And this Principia Mathematica, it comes in 3 volumes. Whitehead was the advisor of Russell, and at the same time David Hilbert, he was working on formalizing things in terms of finistic proof systems. Proof systems should be finistic. Things are finite, eventually they are finite and stuff. These kind of things. This finistic term that he introduced in his literature, it stays vague till today. He did not define it very formally and it's still vague. And then, in parallel to David Hilbert, there is a big name that you have heard, George Cantor. He actually destroys everything that David Hilbert was doing. What he discovered, David Hilbert, what he discovered is there are infinities bigger than other infinities, and I will show you that. There are infinities bigger than other infinities. You cannot just get rid of infinity. Not only that, the different infinities, they are infinitely many. Make sense? Oh, doesn't make sense, but we will see that. Then it will make sense. Sahi hai ji? And Cantor proves this through a very famous proof technique, which is now a proof technique on its own, but it is under the umbrella of proof by contradiction. So that proof is called the diagonalization, that technique. We'll study diagonalization at length today. Let me just motivate you why I'm going to do this. So there's Bertrand Russell and Whitehead and all these people. They thought they have devised a system that is contradiction free. It will never derive a false statement. A contradiction free system is some system that never derives, it never proves a false statement to be true. So they do some tweaks with the set theory of Frege, and maybe several tweaks, I don't know, some tweaks, or maybe they have reinvented everything, whatever. But when they introduced theory of types, they were hopeful that now things are very well organized, and that's the system one should use. If something cannot be stated in the system, let's make the system rich and allow each and everything to be stated in the system. Once stated in the system, in the language of our system, then it should be proven. Otherwise, we will not accept the claim. So the properties of a mathematical proof system. One property is it is highly expressive. It has language that is able to express a lot of different things, actually all of different things, ideally. You should come up with the language, symbols and stuff. Then there should be some rules of inference which tell you from this statement, that's how you can deduce this one, and that's how you can deduce this one, and so on. And then there are some rules to start with called axioms. Some statements that are true. No arguments. True. Make sense? Today it makes sense saying that -1 square is equal to 1. Well, that makes sense because you have applied this so many times and you are reluctant to say this is wrong. But that's a rule, it has no proof. It's true. There is something, yes.
In the beginning you said everything in the universe has a proof. Can I give us the hair is not a proof?
So when you drive a system, you have to start with some things that are intuitive. And you say, okay, let's accept these things are true, and then drive everything else.
So something that intuitive just now देखते ये चीज़ होती आ रही है, but you won't accept it unless you give it a mathematical proof. Axioms are like that.
So no.
So why is that?
So axioms. So without this thing, you can never come up with a system. So that's an agreement that we will start with some rules, and everybody will be agreed on that. If there is a disagreement, we will settle that disagreement. But at the end of the day, there is agreement on some rules that are called axioms. That's it.
So if in the future someone thinks that axioms say नहीं है, so they will improve it and then accept it as a
So that was a property of mathematical system. Once you establish the axioms to be true statements, then that system can never contradict it through other axioms. because the mathematical proof system you are going to develop, it is contradiction free. At one time you are saying this is true, but then your system evolves and then it says, oh, that is not true. That means your system has contradictions. And when they develop systems, they avoid contradictions. And these Russell people, they were trying to develop such a system. So axioms are there. Without axioms, you cannot start. Like, just to take an example, like people just said that 1 over of a cricket match has 6 balls. Why? Well, it has 6 balls. Make sense? Agreed. Everyone agreed. At least the cricket makers, they designed this rule and everyone agrees. Now based on this rule and some other rules, for example, a one-day match has 50 overs. That's a rule. Might have 45 initially, but now it has 50 overs. That's the rule now. With this first rule and the second rule, you can argue about the following statement, whether it's true or false. The statement is, in one-day match between team A and team B, team A has played 450 balls. That's false. Make sense? Because 1 over has 6 balls in total, and there are 50 overs in total, so one team can play at most 300 valid balls.
No ball with
Valid balls. Valid balls. Yes? Make sense? So let us counting the valid balls that they play. So that is false, accepting those two axioms. So that is like cricket system. Yes? So, what is the desirable property of a proof system? A system that validates the claims. Because we want to validate the claim through logic, through reasoning. These rules of inference, they are reasonings. We want to do that. The desirable properties are the following. Property number 1, it is sufficiently expressive, rich enough to express any phenomenon, or most of the phenomena. Maybe one system is more richer than the other and so on. It has so many, or maybe some, or it has some rules to start with that are true. And there is some rules of inference in there. Yes? But having this defines a mathematical system. Having these, so the most important property that you should focus is expressiveness. How many different phenomena it can express in its language. Mathematical system is a language. Sahi hai? Expressiveness, axioms are there, rules of inference is there. Second property is contradiction free. Because it's a proof system, you are thinking that I will bring everything in front of the judgment seat of reason, and then I will reason everything. Well, that judge should be contradiction free. It never said that something is true one day and then another day that the same thing is false. It should not do that. Make sense? We call this property of a mathematical system that it's contradiction free, or precisely, it never drives a false statement. It never proves something that was false. It never proves it true. It never proves a false statement, or it never drives a false. Derivation is simply you start with something, you apply rule of inference, you drive something else, nothing else. And then it should not be the case that you end up with a false statement. You can never be able to drive a false statement. Yes? This property of a proof system or a mathematical system is called consistency. So consistency. Your mathematical proof system should be consistent. It should not drive a false statement ever. Yes? Second property, it should be complete. Complete means a a mathematical system or proof system is called complete if it drives every true statement. There is no true statement that is not drivable in the system. You bring a true statement, it is drivable in the system. If the system is able to drive every true statement, then the system is called complete. Yes.
Do you agree that axioms are true statements?
Yes.
Does a complete system derive those axioms?
So we never talk about driving those systems, driving those axioms. होता ये है कि there are some independent systems and dependent systems. Independent systems वो होते हैं कि आप जब rules place कर रहे हैं, axioms जब आप place कर रहे हैं, these axioms, one of those axioms is not drivable by the rest. Because if one axiom is drivable by the rest, then that axiom is not needed to start with. So, but even if an axiom is derived through other axioms or through the statements that were derived through axioms, that's okay. Axiom was a true statement at the start. That's okay.
And you mentioned the word rules of inference
Yes.
proof system. So what kind of rules of inference are you talking about जब आप एक system develop कर रहे हैं?
So for example, like you have studied these rules of inference, like in logic P implies Q. That's a big rule. That's one rule, for example.
तो जो भी आपका प्रूफ सिस्टम है वो जो आपने अपना पहले ही एक यूनिवर्स ऑफ डिस्कोर्स तय कर लिया वो तो उसके अंदर ही वैलिड हो गया तो ये उसकी एक पहली लिमिटेशन नहीं आ गई कि वो वैलिड ही सिर्फ अपने यूनिवर्स ऑफ डिस्कोर्स के लिए तो वो एक कंप्लीट तो कभी भी ना हुआ कि मैं कहूँ कि वो एंटायरिटी के लिए वैलिड है जबकि मैंने पहले ही अपना एक यूनिवर्स ऑफ डिस्कोर्स तय कर लिया कि मेरा प्रूफ सिर्फ इतने के लिए कंप्लीट है.
So ideally, if you want to make that system, these should be the properties. What you are saying is exactly the conclusion of the talk. So hold on. So you're talking correct. That's all.
Sir, is it true that anything in every proposition in the universe can be changed into mathematical notation and then be proven?
We want to build such a system. We want to build such a system. We want to state everything in that
So
way.
your such argument is that atom is the smallest element that exists, the most fundamental element. Can that be proven?
It should be, if it is true.
How is that proven? Why did we accept it? क्या अगर कोई argument नहीं था, and if we did accept it, तो गलत क्यों prove हुआ? Why was it wrong?
You're talking like anti-logical positivist. Not everything is provable and stuff like that. मेरी बात समझ में आई?
I get
You're
it.
talking like that.
But
And I will show you that that's possible.
The systems limit creativity.
Sorry?
We are limiting ourselves to
Exactly.
our thoughts.
Yes.
So this system is actually creating a limitation to our thinking, our creativity.
we're going against the idea that we can be wrong.
So then how can we prove
I'm
claims?
just saying sir कि अगर हमारे axioms wrong है तो एक मतलब हमने पूरी दुनिया ही डिस्कवर नहीं की
Precisely.
हम सोच ही एक तरह से है तो अगर हम उस सोच को लेट से for instance थोड़ी देर के लिए forget कर देते हैं और किसी और तरह से सोचना शुरू करते हैं तो हम कुछ और डिस्कवर कर सकते हैं टेक्नोलॉजी से अलावा हम कोई और चीज़ें डिस्कवर कर सकते हैं तो ये तो लिमिटेशन ही कर रहे हैं अपने ऊपर हम खुद ही
Well, that's your intuition, that's your belief, your faith. I don't accept it.
सही बात है,
ये
but
logic
people believe in flat earth.
asking logic
But people, like a lot of people believe in flat earth theory, doesn't make it true. That's an agreement, that's an axiom for them, but it doesn't make it true.
देखिए एग्रीमेंट ये नहीं है कि जैसे ये 6 balls होंगी तो यही होंगी. मैथमेटिकल सिस्टम में there are things that are very much intuitive, like once you have defined a symbol 0, once you have defined a symbol 1, then an axiom is 0 is not equal to 1, or there are not two different, for example, numbers that are different numbers and at the same time they are same. I mean, these kind of axioms that intuitively make sense. अब अगर आप कहते हैं कि मैं कुछ और चीज़ें डिफाइन करूँगा वो एग्रीड तो हैं लेकिन लेटर ऑन वो प्रूव हो जाएंगी कि वो सही है या नहीं है, वी डू नॉट नो, तो मैं उस सिस्टम की कंसिस्टेंसी और कंप्लीटनेस के बारे में क्लेम भी तो नहीं कर रहा. जब मैं मैथमेटिकल सिस्टम की बात कर रहा हूँ जो एक आइडियल सिस्टम होगा जिसको मैं बनाना चाह रहा हूँ, तो बनाने वाले की ख्वाहिश क्या है, लॉजिकल पॉजिटिविस्ट्स की? It should be expressive, everything should be expressed in that language. I am suggesting a language, I am coming up with a language, and that language, what are the properties in that language? It should be expressive, rich enough. Second, it should be consistent, never drives a false statement. Once certain axioms are there, once certain rules are there of inference, so derivation starts. It never drives a false statement. 3, it should be complete. It should be able to drive every true statement. अगर ऐसा सिस्टम आप बना लें, अगर आप ऐसा सिस्टम बना लें जो कि ख्वाहिश थी बड़े स्टार्ट में और लोगों ने अटैम्प्ट्स की इसके ऊपर और अटैम्प्ट करते चले जा रहे थे, तो फिर ये एक ऐसा सिस्टम होगा जो दुनिया के हर क्लेम को थ्रू लॉजिक अप्रोच करेगा, बिकॉज दैट्स अ लॉजिकल सिस्टम. कोई भी क्लेम है, अगर वो ट्रू है तो वो, अगर वो ट्रू है, अगर आप लेके आते हैं कोई स्टेटमेंट कि यार सूरज जो है वो ठंडा होता है, क्लेम है, well okay, that's a claim, I will express that claim in my language. If this is true, it should be derived. If it is not derived in my system, I will not accept it. So that was an attempt कि all the understandings, all the approaches to everything can be reasoned through logic. Whatever that is not in that, we will not accept that.
What if your system is faulty?
What if?
Your system is faulty.
I don't wish to build such a system. मैंने अभी तक ये नहीं बताया कि इस तरह के सिस्टम बन गए हैं, मैंने अभी तक ये नहीं बताया. ये जो आपके अंदर वो आ रहा है ना, यार ये सिस्टम, इसमें ये मसले हो सकते हैं, वो मसले हो सकते हैं, and so on. That is exactly what I'm going to talk about.
Does the perfect system exist?
Well, what do you mean by perfect system? It is rich enough. So let me write the properties of a perfect system. It is rich enough. Where rich enough means is that it's rich enough? That's a property. It's consistent and it's complete. Such a system you call as a perfect. Yes? So now your question is in 2019, your question is, does such a system, one system let's say, exists? The answer is no. And that was proven in 1931. And I'm going to show you that proof today. Again, I'm saying, whatever you're thinking, there's a proof of it. मज़े की बात ये है, जो इनिशियल सिस्टम्स थे ना, जिनको कंसिस्टेंट और कंप्लीट माना जाता था, नंबर थ्योरी के सिस्टम्स, पियानो और अरिथमेटिक के बारे में शायद आपने नाम सुना. ये जो गर्डल है, ये जो मैं आपको बात बता रहा था, ये रसल और ये सारा काम कर रहे थे, कर्ट गर्डल, ये एक लॉजिशियन था. ये आया और इसने कहा कि whatever you are attempting, जैसे आप कह रहे हैं ये तो यार हो ही नहीं सकता, कोई और दुनिया होगी वो हम शायद डिस्कवर ना कर पाएंगे. उसने इस तरह की बातें नहीं की, ऑल्दो लग रहा था कि यार ये सही कह रहा है, ये नहीं है, लेकिन वो कहते थे ऐसे प्रूव करें इसको. उस बंदे ने उनके सिस्टम के अंदर बैठ के ये प्रूव किया कि योर सिस्टम इज नॉट कंप्लीट. That was not his intuition, that was not his imagination. So whatever you want to prove, come into the system and then prove. उस सिस्टम के अंदर क्या? नंबर थ्योरी के अंदर, नंबर थ्योरी that talks about integers. Yes.
सर उसने मतलब अंदर कॉन्ट्रडिक्शन का, सिस्टम के अंदर कॉन्ट्रडिक्शन.
उसने ये कहा था, उसने इन तीनों चीजों को ना if then else में कहा. उसने कहा अगर एक सिस्टम रिच इनफ हो, अब ये मैं क्लेम बता रहा हूँ जिसका प्रूफ हमने करना है पूरे रेस्ट ऑफ द लेक्चर है कितना.
We have 2 classes.
Okay, so I guess I have sufficient time. Let me build the ground and then math will follow. No problem. So you agree that these are the properties of a perfect system?
Science based.
You agree that these are the properties of a perfect system or ideal system? He said what he proved is, his claim is the following. If your system is rich enough, then both these properties for that system, both these at the same time cannot be true. If it is rich enough, it can state everything. It can state everything in the language. Then either it is consistent or complete. If your system is highly expressive, और ये बात उसने उसका belief नहीं है, ये उसने system के अंदर जाके किया. Let me just state and then I will. If your system can state a lot of things, ideally everything, then to stay away from contradiction, there will be some true statements that are not drivable. No, these are not axioms. If your system is rich enough means it can state a lot of claims in its language. It is expressive. Yes? If it is expressive highly, then that system will be attacked by either inconsistency or incompleteness. For sure. One of them will attack the system and the system will destroy it. Yes.
So doesn't that mean that we messed out an axiom? It means that the axioms that we have to write, we have missed an axiom, so we can